Hello, welcome to the course Electronic System Design. In the earlier lectures, we were discussing about the combinational logic circuits where we have some logic gates and we implement a function using these logic gates. The property of these combinational circuit is whatever is the instantaneous input of these logic gates, the output depends only on that present state of inputs. So, in combinational logic circuits, then we have two types of gates. One is the static gates and one is the dynamic logic gates. So, we were discussing the static logic gates. We saw that sometime the delay of the logic depends on so many factors. For example, the resistive nature of pull up and pull down and the load capacitance CL what is connected at the output, and also sometime the delay is dependent on the input pattern itself. So, depending upon the input pattern, because the logic circuit can have more than one inputs, it can have like 3 or 4 inputs. That time the overall delay or the worst case delay of a circuit is dependent on the input pattern as well. For some input pattern the delay is less, for a particular input pattern the delay is the maximum, and we call it the worst case delay, and the best or the least delay we call it the best case delay. So, these numbers are very important, the worst case delay and the best case delay, because this gives us a time frame or the time window over which we cannot say that the data is stable or the output has settled down to its final value or not. So, only after worst case delay we can say that the output is now stable, and now it is completely dependent on whatever is the current input pattern is. Before worst case delay we cannot say whether the output has made a transition based on input or not, because it may be possible that input has changed and the data is still traveling in the circuit to arrive at the output. So, we have worst case delay. Then we saw some design techniques on a particular CMOS circuit, that how can we improve the delay or make the circuit fast. So, those are the design techniques we were discussing, and in the first design technique we saw that we can progressively increase the size of NMOSs. For example, if we have series of NMOS in the pull down ladder, we can progressively scale these MOSFETs. The nearest to the ground is made the biggest one, then on top of it smaller than the earlier one, and then again smaller and smaller, so that we were saying that M1, M2, M3, M4 are the stack of NMOS, then M1 is greater than M2, greater than M3 and greater than M4. So, this is how we can design a CMOS logic circuit, so that the overall delay of this logic circuit is minimum. Today we are going to discuss another technique where we have the delay which is dependent on the input pattern as well. We have a stack of NMOS in the pull down ladder, and now because we have stacks, so we have multiple inputs A, B, C. So, depending upon the input pattern of A, B and C, the delay is dependent on those pattern, and how to improve the delay based on this input pattern. So, let us discuss this design technique. In this technique, for example, we have a stack of NMOS in the pull down ladder. So, I am just drawing the pull down ladder only. In pull down ladder we have 3 NMOSs connected in series. And this is the output node which is connected to load capacitor CF. Now we have, let's say, 3 inputs here. This is input 1, this is input 2, this is input 3. So we have 3 inputs now. Let's call these transistors M1, M2, M3. As we discussed earlier, whenever there are two terminals which are joined together using a wire, that creates a additional node in the circuit, and these additional nodes will have some parasitic capacitance as well. So in this circuit, if we see carefully, we have two additional parasitic capacitance which we are drawing through this green color. So we have additional capacitance here, let's call it C1, and one more additional capacitor here, let's call it C2. Now in this circuit, what we say that for these three pattern, input 1, input 2, input 3, we have input 3 which is stable at 1. So this state of IN3 is 1. Input 2 is also 1. And input 1 is actually making a transition from 0 state to 1 state. It means input 1 is rising from low to high. So what will happen when this is initially at 0, input 1 is 0, it means this M1 was off and this M2 and M3 were on because input 2 and input 3 are high. So M2 and M3 were on, it means there is a resistive path from this output till this node between M1 and M2. So initially when M1 is off, whole of this ladder is actually charged to some initial value. So this capacitor, load capacitor, was initially charged, and these C1 and C2, they were also charged because M3 and M2 were on. So this charge from the output can travel to C2 and can travel to C1 as well. So this C2 and C1 both are charged. So this is the initial condition where we have this Cl which is charged, and C1 and C2, they are also charged at time t equal to 0. Now this input 1 is changing its state from low to high. It means this M1 is now going to turn on. As soon as this M1 will turn on, the output node will be pulled down to 0 because M2 and M3 are already on. So if M1 turns on, this output node out should be pulled down to ground. To do this, this M1 transistor has to discharge 3 capacitors because Cl is already charged and C2 is also charged initially and C1 is also charged. So all these three capacitors are already charged to a high voltage, and this M1 is now have to discharge all of these capacitance, which is going to take time because M1 has its own limited current. So based on that current only, this can discharge all these capacitors, so it's going to take time. So now in this pattern, when input 2 and input 3 are 1, input 1 is making transition from 0 to 1. Then we have critical path for this circuit, which is something like this, that this is the critical path. Critical path is the path where we have maximum delay in a circuit. So this is shown here as the critical path, and the delay is determined by the time to discharge CL, C1 and C2. So the overall delay is determined by time to discharge C1, C2 and the load capacitance CL. So all of these three capacitance need to be discharged to calculate the overall delay, which is going to be high because C1 and C2 and C3, these all three capacitors need to be discharged through M1. So this is the problem where we have a critical path which is coming from input to the output, from IN1 to output node, and we have to discharge C1, C2 and CL. However, if we look closely at this circuit, and if we know a priori that input 1 is the input which is going to be changed very fast compared to input 2 and input 3, generally this information is sometime available at the system level. For example, input 1 is a clock and other input 2 and input 3 are very stable kind of data which sometime comes in from a slow electronics or the electronics which is not functioning very fast. So in that case, if we rearrange these MOSFETs in such a way, the input 1 is applied to MOSFET 3 and input 3 is applied to MOSFET 1. In that case, we need not to discharge all C1 and C2 because they are already discharged at the time 0. When transition is happening at input 1, that time only CL is charged and this MOSFET has to discharge only CL, the load capacitor. In that case, the time required to discharge CL is less compared to discharging CL, C1 and C2. So, if we rearrange the MOSFET in such a way that MOSFET for input 1 comes to very close to the output node, in that case we have lesser delay in the circuit and the critical path is little slower than this critical path. So, let us see that in this circuit. So, if I draw the same circuit, but now rearranging the transistor ordering, this is load capacitor, These are the transistor. Now the input 1, instead of at the bottom, right now at the top. So IN 1 and I apply IN 2 and IN 3. So I am just reordering the transistor, or we can say reordering the input signals. These transistors I am assuming same. And now input 3 is, as we said, already 1, input 2 is already 1, and input 1 is making a transition from 0 to 1. We have these similar stray capacitances C1, C2, but if we see this at time t equal to 0, when input 1 is already at the 0 level, we have input 2 which is 1, input 3 which is 1. It means the M1 and M2 are already on. If they are already on, this C1 capacitor is already discharged to ground. So the initial value at C1 is discharged. Similarly, C2 capacitance, this is also discharged through M2 and M1 because M2 and M1 both are on. So this node is going to discharge to ground. So this value of C2 is already discharged. CL is the load capacitance which is initially charged because M3 is off. So this is charged. So now when input 1 is transitioning from 0 to 1, it means M3 transistor will now turn on. When it turns on, it has to pull the output node to ground. Now in this system we have these three capacitance and two are already discharged at time t equal to 0. Only CL capacitance need to be discharged to ground by the ladder M3, M2 and M1. So here if we see overall, this delay will be lesser than the earlier case because only one capacitor is charged with the same amount of current which M3 can provide. Now we will have the lesser delay in this case. So now we can write the overall delay is determined by time to discharge only CL. So here we have the critical path which is from this input 1 to the output 1, and this has definitely the lower delay value compared to the earlier critical path. So this is one of the technique by which we can reduce the overall delay of a CMOS circuit by just reordering the input pattern what we apply on the circuit. So we can either rearrange the input pattern or we can just swap the NMOSes from low to bottom with its input, and we can see the critical path actually changes and overall delay is lesser compared to the previous stage. So this is one of the design technique people use to make a very fast transition signal, if there are 3 signals coming in and you know that one signal generally switch much faster or more frequently than compared to the rest of the signals, then you apply these signals intelligently in such a way that fast signal is closer to the output node and the slow signals are little on the bottom, input 1 as input 2 and input 3. So, they are close to the ground. So, this is one of the technique. Another technique we can think of, that when we have these gates, for example, we are talking about 3 input gates, we can have 4 input gate as well, 4, 5 input gates. So, when we have these 3, 4 input gates, all these are connected to the previous stage. All these gates which are connected in these MOSFETs, these offer a capacitance to the previous stage, because this is gate capacitance. The gate is the terminal where we are applying input. So, gate is nothing but a silicon oxide layer which act as a capacitor. So, this capacitance is kind of loading the previous device, and because of this capacitance, the CL of the previous stage actually increases, and our overall delay depends on two things. One is the load capacitance and the resistance of pull up pull down network. So, by having more number of inputs, we are actually increasing the load capacitance CL, which is again going to degrade my delay, or delay will be higher. So, instead of having a gate which is 4 input gate, if we can somehow design our logic in such a way that we are using only 2 input gates. So, in that case, though that the gate count will be higher, but the overall delay can be smaller compared to this 4 input logic gates. So, let us see this concept now. Design technique 3 for fast CMOS gates. So, in this technique we can actually find some alternate logic structures. To reduce overall delay. So, let us take an example. For example, we have a function f which we are implementing, and this is nothing but depending on the 8 input signals, which is, let us say, A, B, C, D, E, F, G, H. So, let us say this is A, B, C, D, E, F, G, H. These are 8 input signals, and what function I am implementing is just the product of all these inputs. So, this is nothing but AND of all these 8 signals. So, the one option is I make a 8 input gate which can do the AND operation. So, that I can do using universal, let us say, NAND gate. So, I make a NAND gate, it is going to be a big NAND gate, which has 8 inputs, and because this is NAND gate and we are calculating AND, so we will invert the logic after this using a small inverter. This is like this. Signals are here: A, B, C, D, E, F, G, H. All these signals are applied here, input of NAND gate. So here you will get F bar, and after this inverter we are producing here the function F. Now if we closely see, because we have so many inputs, it means we have a stack of NMOS which is 8 transistors on top of each other, and these 8 capacitances, 8 gate capacitances are going to load my previous device and act as a CL, the load, output load to the previous state, which is going to degrade my gate delay. For such a big logic gate, let's assume that we have a delay of, let's say, 10 picosecond, just an example. So this is 10 picosecond, and let's say further inverter has 1 picosecond of delay. It's just an example number. So overall delay we have here which is 10 plus 1, 11 picosecond. So this is the overall delay of this logic circuit, which is very high. However, if we can do some Boolean algebra, there is techniques of Boolean algebra through which we can reduce the logic to using some other gates. So if we implement the same function using different gates, let's say I want to do it only with 2 input gates and I have NAND NOR gates available with me. So this is how I can implement the same function. I have 2 input NAND gates, these are now connected to NOR gates, and further these gates are connected to one more NAND gate, and then finally an inverter. So here we have these signals. This is our F bar and this is our final F. So now if let's assume that all the gates, all the two input logic gates have delay of 2 picosecond, then we can write the overall delay. For example, this is going to produce 2 picosecond delay, this is going to produce 2 picosecond delay, this is 2 picosecond, and inverter is, as we took earlier, this is 1 picosecond. So let's say this 2, If we see any path from the input to output, now what is the overall delay? Let's say from A to F we calculate. So first the signal will go here. This is 2 picosecond delay. Then further here it's 2 picosecond delay. Then further here 2 picosecond delay, and then 1 picosecond. So the overall delay is actually 2 plus 2 plus 2 plus 1, which comes out at 7 picosecond. So here we can see, just by implementing the logic by using different logic gates, we can reduce the overall delay from 11 picosecond to 7 picosecond by using some Boolean algebra. So by Boolean algebra we can reduce the logic in such a way we use only 2 input logic gates. So this is one of the technique we use to optimize the logic delay. So here we have seen some logic techniques or some design techniques through which we can optimize the delay of a logic gate. So we saw some design techniques. For example, this is Boolean algebra you have to apply on the implemented function and simplify it such a way that the overall delay is less, or we can do ordering of inputs. So that technique we saw. So till now we were discussing about the static CMOS gates, where the pull up network and pull down network, they are dual of each other. Pull up network is on, then pull down is off, and vice versa, and the output node is always connected to supply or ground. So here we saw all these design technique, but there is a slight problem in the static CMOS gates, or we can say the disadvantages. When the signal make a transition, then there is a time when the signal is transitioning, which is not stable at low or high, it is still in between. That time, for a very short amount of time, pull down network can become turned on, and pull up network is also turned on because the signal is still in between. So during that small time where pull up network is on and pull down network is on, there is a short circuit current which can flow from the VDD to VSS. This is called the dynamic power dissipation, because when gate is transitioning, when there is a dynamic activity is there, that time if there is a current flowing, there is a power dissipation, that counts to the dynamic power dissipation, which is very significant considering how slow the input transition is. If the input transition is very slow, then this time is very long, for which the both pull up and pull down are on, and this will give to considerable amount of dynamic power dissipation. So this is some of the disadvantage of static CMOS gates. So let's now consider the next type of gates, which are dynamic logic gates, which are little different than these CMOS or the static logic gates. So let's consider the dynamic logic gates. So unlike the static logic gates, in dynamic logic gates we do not have pull up network. Here we just have one clock which applies to a single PMOS. This single PMOS acts like a pull up network, and in pull down network we have all the logic. Whatever function we want to implement, that is implemented using the pull down network. So we have dedicated pull down network, This is clock. Below this pull down network also we have one more clock, this NMOS transistor which is connected to clock. And this pull down network is designed very similar to our static counterpart, static logic gates, where we apply inputs as IN1, IN2, IN3. So this is the basic architecture of dynamic logic gates. So how this dynamic logic gate works? In static CMOS gates, if we remember, the output node which is connected to load capacitor, this output node is always connected to VDD, supply voltage, or ground through these pull up transistor or pull up network or pull down network all the time. In dynamic logic gates, we have a separate signal which is called clock. So now what is the function of this clock is, in dynamic logic gates we charge the load capacitance CL. CL is a capacitance. So we charge this CL capacitance using clock before every operation. So before every operation, we let us say clock will come and our output node will be charged to VDD. Now when the input will transition, input 1, 2, 3, based upon the input condition, the output can be only two values, either it should be high or it should be low, based upon whatever input comes in. So if this is high, then input pull down network will be such a way that pull down network will not turn on because of that input pattern, and my output will remain high for that particular input pattern. If the input pattern is such a way that output should become low, that time the pull down network will turn on, and this output capacitance, which is actually pre-charged in the previous cycle, this output node will be discharged through pull down network, and then we have a NMOS at the bottom. So we are now talking about two stages. One is the pre-charge. Pre-charge is the state where inputs are not transitioning, only clock is doing its work. Clock is pre-charging this load capacitor CL. Then the input pattern will come. If input is such a way, output should become 0, then pull down network will turn on. If the input network in such a way that output should remain high, that time pull down network will not turn on, and this output is still isolated. Whatever capacitance, whatever voltage, whatever charge it is having on the capacitor, that will remain there. So it will remain high. So this is how a dynamic logic gate works. We have two cycles. One is the pre-charge cycle, where we pre-charge this node, and then the actual evaluate cycle, where we evaluate what the logic should be, either it should be 0 or 1. If it should be 1, pull down is not doing anything, it is just still the same as previous state. If the output is 0, it means the pull down network is turned on and this capacitor will discharge to ground. So this is how dynamic logic gates work. Now let us see through a circuit how does it look like in actual implementation. So we have basically two phase operation here. One is the pre-charge, when CLK is 0, and then the second step is evaluate. This happens when clock becomes high. Let's take an example. This is our PMOS transistor on the top, which is our pre-charge transistor sometime we call it, and we make it very thick or very large in the width so that it can immediately charge the load capacitor. So this is MP, which is connected to clock. Then we have any logic, this is the output node which is out, and the function it is implementing is AB plus C whole bar. So here if we see, during the first clock cycle when the clock is 0, that time this PMOS MP is on and the output will be charged to high value through this VDD, and at that time, because clock is low, this time when the clock is low, this NMOS is off. It means this output node cannot discharge to ground. So whatever is the charge coming from VDD, that will charge the output node capacitance. We have certain capacitance at this point, is going to charge or pre-charge this output node. When the clock becomes high, this is the evaluate region. This time this PMOS is off. It means there is no charge now coming from VDD, and this capacitor which is already charged, this is now discharged through pull down network, which also has this clock. So clock is high, it means this NMOS will turn on from off to on, and this pull down network is going to discharge this capacitor. So based on this circuit architecture or the general architecture of this dynamic gates, we can think of 2-3 points or the properties of these dynamic logic gates, that the function whatever you are implementing A, B plus C, this whole bar, that is implemented using only the pull down network. Pull up network is always a single PMOS transistor. So all the circuit whatever function you are implementing, that is only through pull down network. So it reduces the number of transistors needed to implement a function. So PMOS, we are not using any PMOS devices, only for one, and only pull down network need similar amount of device as static logic, and still we have full rail to rail swing. The output is discharged completely to ground and charged completely to VDD. So let us write down these few properties of these dynamic gates. So the first one is logic function is implemented by the pull down only. It means we need only n plus 2 number of transistors, where n is the number of inputs coming in, which is compared to 2n, which is needed for static CMOS logic gates. So the number of transistors needed is n plus 2. We can write we need 2n in case of static coils. So this 2 comes from one additional PMOS we have on top and one additional NMOS we have at the bottom for clock signal. The next point we can notice here is we still have full output swing. It means our noise margins are still very good. Still we have ratio-less design. The sizing of device does not affect the logic level in a steady state. We have faster switching speed. This is very important point here because this faster switching speed comes from multiple factors now. The one is because the load capacitance itself is reduced because we have now only n number of transistors connected at the previous state. So it reduces the input capacitance itself is lower. So we have faster switching speed. So in this dynamic gates, we have reduced load capacitance. Second, we have reduced load capacitance because of smaller output loading. And third, there is no static current in the circuit, because when we have pre-charged clock, then the load is pre-charged and then the PMOS is turned off. So even that input signal is transitioning, there is no time window for which pull up network and pull down network both are on. So we do not have any short circuit current from supply to ground. So all the current by PDN goes into discharging the CL. So we have some more property of these dynamic logic gates. The next one is the overall power dissipation usually higher than the static CMOS sometime. So this is because we have higher transition probabilities and we also have extra load on the clock signal. we also need a pre-charge or evaluate clock. So these are some of the properties which we have for dynamic logic gates. The function which we are going to implement using dynamic logic gates, this is implemented only by the pull down network. Pull up network is not needed at all. Only one extra PMOS we add for the clock signal. So the transistor count is less. We only need n transistors for n input gate. So the total transistor count is n plus 2. However, in CMOS, the static CMOS, we have pull up network and pull down network. So n and n, there are 2n logic gates needed. So when we need large number of gates, it means we have more gate capacitance which we are connecting to previous stage. So because of this extra gates connected to the node, we have extra capacitance which is going to degrade the delay sometime. So that is one property of dynamic logic gates. The second is we still have full swing, the output is completely charged to VDD, and when this is discharged, this is completely discharged to ground. So if we have rail to rail swing from 0 to high and completely high to low, then we have very good noise margins. So that is still there in the dynamic logic gates, despite we have less number of transistors we are using. Still a ratio less design, because the output in the steady state condition, it does not depend on the ratio of pull up network or the pull down network. This is completely 0 or 1. So this is still a ratio less design, and this offers sometime the faster switching speed, because the load capacitance is much lower at the previous stage, because we have less number of transistors. However, in dynamic logic gates, we have a pre-charge clock, which is an extra circuit we need. There is a extra routing for a pre-charge clock for all the gates. So that adds up to the power consumption of overall system. Next is this pre-charge need to be timed very carefully, because these output nodes where we are storing the charge in the pre-charge cycle, this charge can leak away if we the clock remains idle for a long time. So there is a timing consideration while during pre-charge and evaluate cycle, which we need to simulate it very carefully, so that this charge is not leaked away, and this is discharged only through the PDN network in evaluate stage. So this is all for today. Thank you.